Alright, so now what we're going to do is we're going to look at the first derivative test for relative extrema. Okay, now recognize that what we've done so far in Chapter 4, if I want to find global extrema and I know that I have a function that is continuous and on a closed interval, I would use EVT. In the first part of this packet, we were reviewing what increasing and decreasing and constant means for a function, and we were doing a test for increasing and decreasing using the derivative, because obviously it's going to be important where an extrema is to know where you're increasing and decreasing. So we did that test. Now that we've determined where a function is increasing and decreasing, now we're going to do the first derivative test for relative extrema. Now, notice that first thing that we're going to have here is that x equal to c needs to be a critical value of a continuous function. So a critical value of a continuous function, remember that we're looking for when the derivative f prime of c is equal to 0, or the derivative f prime of c is equal to does not exist or undefined, right? We're taking care of our nice hills and valleys here. These are our critical values because of that. And where the derivative is undefined on a continuous function, which means that it existed on the original function, f of c exists, is either going to be a cusp or a vertical tangent is involved in there. Okay? And so it's going to be a critical value for a relative extrema. Now, not all places where I have a 0 or an undefined is going to be a critical value, is going to be a relative min or a relative max, because that's not what's important. I'm drawing them as relative mins and maxes. However, you could have a 0 that looks like this, where you have a horizontal tangent line here, or you can have a cusp where it comes in and then does something like that, where these are not extrema. So the critical values are critical because they're going to be candidates for relative extrema. And then what we need to do, the test, is that we have to show that the derivative changes signs, that it changes from negative to positive, that the slope before the critical value is negative, the slope after the critical value is positive, and if I can show that, then I have a relative minimum. So I use the test for increasing, decreasing to determine that part, and then I am going to look at whether it changes from positive to negative or negative to positive. If it changes from positive to negative, then we have a relative max, and then if it doesn't change, it's positive on both sides, negative on both sides, then it is neither a relative min or a max. Okay? So again, here's our visualization. Here's where we had a nice f prime of x. C is a critical value because f prime of c is equal to 0. It has a horizontal tangent. So at the critical value, if I were to look at the derivative before the critical value on the function, I would see that I have a positive slope. For the derivative after the critical value, I have a negative slope, and because it switches from positive to negative, at x equal to c, there is a local max. Now notice this doesn't give me the max value at c, it only tells me there is a local max at x equal to c. Likewise, if you switch from a negative derivative to a positive derivative at a critical value, and c is critical because the derivative was equal to 0, I get a local min. Now, and it doesn't matter why it's a critical value. Again, just to show you kind of a additional caveat here. If my function was increasing and then decreasing like this, and I have c is critical, this case c is not critical because it's 0, it's critical because it is undefined because of the cusp. But before c, the derivative of all the values before c is positive. The derivative of all values after c is negative. And because it switches, this is going to be a local extrema. Okay? And same thing true over here. We could draw a picture with a cusp that goes with that. If it doesn't switch, so here's an example where I have a critical value, f prime of c equal to 0, but the derivative before is positive, the derivative after is positive. It doesn't switch signs, and clearly you can see that this is not an extrema. So it is very, very important as we are looking at this that when we're using the first derivative test to justify our relative extrema, we want to make sure that we get the sign change. It's the sign change and the type of sign change of f prime that is telling us whether it's a max or a min. Okay? The second thing here that I do want to really, really stress to you guys is you need to be very cognizant that you need to eliminate the use of pronouns. Do not say it increases. Say f increases. Do not say because it is positive. You need to say because f prime is positive. F increases because f prime is positive. Don't say f increases because it is positive and immediately you won't get credit because it does not refer, you don't know what it refers to. It's ambiguous. So you want to make sure you're showing us that. Alright, so let's look at example 5 here. So example 5, we're looking for the x-coordinates of local extrema. I'm underlining this because as soon as I see the word local, I know that this is not EVT. Don't fall into the kind of mistake that you go over here and you go, hey, I have a continuous function, and f is continuous on the closed interval 0 to 2 pi. Okay? When you're looking at it, it's a nice and simple continuous function. Continuous linear, continuous trig, combination of two continuous functions. And so you're like, hey, I'm going to use EVT. And I'm like, no, you're not looking for EVT is for global extrema. Global. This is not global. We're looking for local extrema. And remember, local extrema cannot be endpoints. Cannot be endpoints. So we are not even considering endpoints at all in this. We're looking for values within the interval 0 to 2 pi for which they are local extrema. So since we have a continuous function, we're going to look for our critical values first. Our critical values, we find the derivative, f prime of x, 1/2 minus cosine of x. And because this is, if you weren't sure of this, we would look at it, but you want to find your critical values, you have your options. You want to know when is f prime of x equal to 0. So f prime of x equals 0 when 1/2 minus cosine of x equals 0. Cosine of x is 1/2, and if you know your trig, you would know that that's the pi over 3 family, and so the values in the interval 0 to 2 pi that would be of interest would be pi over 3 and 5 pi over 3. We also know that f prime of x exists for all x in the interval. Okay. Another way of saying this would be f is differentiable for 0 to 2 pi. The reason why I'm mentioning that is because your critical values are where the derivative is 0 or does not exist. So in this case, we don't have any does not exist. Now, once I have the critical values, I am going to test for increasing, decreasing by using my sign chart. I put my critical values on. I'm also going to add 0 and then my pi over 3, and then I'm going to put 2 pi over here, and I'm going to put my 5 pi over 3. The critical values are pi over 3 and 5 pi over 3. However, since I'm only concerned with this section of the graph, I am going to put the endpoints on, and then I'm going to test values to figure out in my derivative, f prime of x, where it's positive and negative. Now we know that at pi over 3, the derivative was 0. So I fill that in, and at 5 pi over 3. Now, we know that, because of the derivative here, let's play around with this. If I were to pick something like the cosine of pi over 6. Now, there's two ways that we can do this. I can look at this graphically, or I can just plug and chug. It does require that you know your trig values and you can estimate. Suppose I pick, since this isn't critical, I'm actually going to do everything down here. 0 I could pick as a test value because that's nice. The cosine of 0 is 1. 1/2 minus 1 is negative. So the derivative is negative for all values down here, including 0. The derivative is positive in here. Suppose let's pick as a test value pi. Okay? Because pi is in between and it's easy to calculate. Cosine of pi, negative 1. 1/2 minus negative 1 is positive. Likewise, over on this section, and again, I'm really only considering close to pi over 3 and 2 pi over 3, because I'm really looking at between 0 and pi over 3 where we start. So at 0 it's negative, and it'll be negative until I hit the intercept. If we test over here, you'll see that again, it's negative. Now what that tells me, again, remember I'm using this as a organizing tool. F of x would be decreasing, increasing, decreasing. All right? Now remember, the sign chart, if I was asked, I would now answer the question about the intervals of increase and the intervals of decrease. However, they didn't ask me that. They asked me to find the x-coordinates of the local extrema. So what I'm going to answer for this, I have enough information now to answer. Pi over 3 is a point on the original. It's defined. It is a critical value where the derivative changes sign. And it changes from negative to positive. So x equal to pi over 3 is a relative min on f of x because f prime of pi over 3 was equal to 0. That made it a critical value. And f prime of x is less than 0 before x equal to pi over 3. And f prime of x is greater than 0 after x equal to pi over 3. Now, sometimes we get a little lazy. I don't want to write that much each time. So we could replace this part right here, the because. Another way of saying this would be to say because f prime of pi over 3 equals 0 and f prime of x switches from negative to positive at x equal to pi over 3. Both of these would be valid justifications for this. All right, of course, we're not done, though. Okay, so it's this or that. That only answers half the question, because not only do I have to find relative mins, I have to find relative maxes. So the other one would be x equal to 5 pi over 3 is a relative max because f prime of 5 pi over 3 was 0, which made it a critical value, and f prime of x switches from positive to negative at x equal to 5 pi over 3. Now notice I did not use pronouns. I did not say it. I didn't say x equal to 5 pi over 3 is a relative max because it was equal to 0 and it switched signs. That doesn't work. You have to say f prime of x. You have to be very clear. All right, let's look at example 6. Find the x-coordinates of local extrema. So again, not EVT. And one thing, you don't really have to say this, but if you want to, you could say, because a lot of times we'll say by the EVT. What we're basically saying here is because by the first derivative test, and then we give the reason for that. Okay. Same thing is true. We're saying by EVT, the following is a global max, because you have to have that kind of information in there. So this is by the first derivative test. All right, so let's take a look at this one. Now I have a polynomial. Again, g is continuous and differentiable because it's polynomial. Right? Notice I don't have an interval here. That's okay. I'm trying to find local extrema. All I'm trying to determine is where I switch, the derivative switches signs, and what are my critical values. So I'm going to come over here. I'm going to find my critical values. I'm going to find my derivative. 6 times 5 is 30x to the 4th plus 4 times 33, which would be 132x cubed minus 90x squared, and then the constant goes away. So we're going to set our derivative equal to 0 to find our first part of critical values. Alright, so that would be when 30x to the 4th plus 132x cubed minus 90x squared equals 0. GCF, I believe we can pull out a 6. So a 6 and an x squared. So I have 5x squared plus 22x minus 15 equal to 0. And now let's see whether we can get this to factor. Let's see, 5x and x. Now we need factors of 15, so 3 and 5. That sounds promising. 3 and 5, so I would have 25 and subtract 3 equal to 0. So our critical values are going to be at x equal to 0, 3/5, and negative 5. F prime of x is never undefined, so we don't have any critical values from that. So now we're going to do our test for increasing, decreasing, just like we did up here. Using our sign chart. Put on our critical values, negative 5, 0, and 3/5. And you do realize that when I do this, scale is not a concern. Okay, we look at our derivative. We know our derivative was 0 in these locations. We determine where our derivative is positive or negative. It's a lead coefficient that's positive of a 4th degree polynomial, so we know that this is plus and plus. We also know that the multiplicity, a little review from Algebra 2, of these two zeros is 1. The multiplicity here is 2 because it has a square on it. So it's going to switch signs, stay the same, and then switch again. You can test it if you want, whether these are positive or negative. That tells me that we have increasing, decreasing, decreasing, and increasing. Okay, so notice that in this test for increasing and decreasing, we had a critical value, but it did not switch signs. So this right now we know is not an extrema. You don't even have to consider that as an extrema. Okay, and again, that's another case where we look at combining these two intervals together because the derivative existed. It was 0. However, because it was a critical value, it didn't switch signs. The derivative did not switch signs. So the function was decreasing and then decreasing, and the point existed, so we can combine these together. But we're answering the question on extrema. And again, remember, they will not interpret your sign chart. This is for you. You now have to answer the question. You would say f of x has a local max, or relative max, doesn't matter, at x equal to negative 5, because by the first derivative test, f prime of negative 5 was equal to 0, and f prime of x switched from positive to negative. Now over here, we're switching from negative to positive, so f of x has a local min at x equal to 3/5, because by the first derivative test, f prime of 3/5 was 0, and f prime of x switched from negative to positive at x equal to 3/5. And let's add that in here, at x equal to -5, because it's got to switch at that point. Okay. Done with that one. Let's do another example, and then we'll take a look at the last page, see if we want to do that in this video. All right, so we have a function that is defined everywhere. It's a continuous function. However, we have a cusp or vertical tangent alert right here, because I have that little cubic root going on. We're going to find the relative extrema. So we are going to find our critical values. So we find our derivative, f prime of x. Use our chain rule, 2/3, x squared minus 4 to the -1/3 times 2x. Put your derivative in a nicer form. Okay, we have our 4x over 3 cube root of x squared minus 4. We now determine our critical values of where we are 0 and undefined. So f prime of x equals 0 when 4x equals 0 or x equal to 0. And f prime of x is equal to undefined when the cube root of x squared minus 4 equals 0, which would be when x equals plus or minus 2. So we have three critical values that are defined on the original one, so they are candidates for relative extrema. Okay? F of 0, f of 2, and f of -2 exist. So they are critical values. Always important to test that. So we're going to do our test for increasing, decreasing, which is basically just organizing our information on our sign chart. We put our critical values, -2, 0, and 2. These were undefined, so I'm going to put u's above here for the derivative. And then, I just thought of something. Yes, I did do it, didn't I? Let's come back here for a second, and let's fix this, because I immediately see, and hopefully you caught it when I was doing this, that to get my credit for this problem, it's g prime of x. This needs to say g prime of x. And so let's just fix this all the way through. Make sure you use the name that they have. See, I'm prone to mistakes just like you guys are. So, let's see, I need to change it. I'm just going to erase it in all the places I have to change it. And then go back and put it in. So we have g of x. That was g prime of x. G of x, g prime of x, g prime of x. There we go. All of a sudden I was like, hey, that was a g in the last one. Alright, so we have f of x and f prime of x. We're going to run our tests now. Also put a 0 there. This is going to be important. Now, when you're going through, it is important to note that it existed here. So, I don't know what you want to say to yourself, but this exists. There is a point there, so we are considering this to be a candidate for an extrema. If this had been a vertical asymptote or didn't exist, I would put VA or hole or something in that location. But it existed, so I'm just not going to write anything. So we figure out whether we have positive or negative. So when we're looking at this, let's plug in a value. Let's do 1, because that's always easy. Positive, top is positive. 1 minus 4, that's going to be negative. So that's going to end up being negative. If I put in -1, I would have a negative over a negative, which is positive. If I pick like -10, I have a negative over a negative, which is positive. And if I pick, say here, 10, positive over positive is positive. So what we know is that we have increasing, increasing, decreasing, and increasing. Alright, we need to fix this one. When I plug in negative 10 and I square it, I get 100. And then 100 minus 4 is positive. So you end up with a negative over a positive, so that's negative. That's kind of caught myself there on a sign chart mistake. Plug and chug error. So we have decreasing, increasing, decreasing, increasing. Alright, now even though this was undefined, this is still a candidate for an extrema because f of negative 2 exists. F of negative 2 exists. It is an actual point on the graph, and it switched signs, so it is an extrema. If f of negative 2 had not existed, it would have not been a local extrema. It would not have even been a critical value. But it existed, so it is a critical value. So our answer here, we actually switch all 3 times. So I would say f of x has a local min at x equal to negative 2 and x equal to 2. Let's get them both at the same time. Because by the first derivative test, f prime of negative 2 equals 0, f prime of 2 was equal to 0, and the derivative, f prime of x, switches from negative to positive at x equal to 2 and x equal to negative 2. So I saved some writing because I can put them, two of them together. And then we would say f of x has a local max at x equal to 0 because, oh, God, it's at the end of a day and I'm getting tired. Your derivative was undefined and f of negative 2 exists, f of 2 exists. So there's a lot of ands in here. I could probably do some commas. I could do a comma here, a comma here, a comma here, and the derivative switches. There's a lot going on in that one. F of x has a local max at x equal to 0 because, by the first derivative test, f prime of 0 was 0, and f prime of x switched from positive to negative at x equal to 0. Alright, so regardless of what's on this next page, I'm going to go ahead and stop there for this video, and I'm going to do example 9 in the next one.